Hello everyone. In this video we're going to do a few more complicated examples of area between curves. Aside from area between curves, I might occasionally ask you to find the area enclosed by several curves. And that refers to the area which is really trapped between all the curves you've been given. I like to think of the curves as just fencing off the area that I'm interested in. Let's remind ourselves of some important ideas from the previous video. We saw that calculation of area boils down to focusing on sample rectangles, such as the one you see here. And we also saw that in order to get the height of this rectangle, it was necessary to consider the coordinates of the points at the top and bottom. In this case, you'll notice the point at the top lies on the red curve, which is y equals x, so the coordinates of that point would be x comma x. But hang on a minute, for this particular region, if we'd chosen to build our sample rectangle somewhere else, then the point at the top would actually lie on the blue curve, which is y equals 3 minus 2x. And that would give us a different set of coordinates. But what that means is that the formula for the height of this second rectangle would be different than the height of the first one. In other words, the formula for dA, the area of these rectangles, would be different depending on which rectangle we look at. And the reason that's happening is because there's this intersection point on the top boundary of our region. The sample rectangles to the left of that point would have their top on the red curve, but rectangles to the right of that point would have their top on the blue curve. And that ultimately means that the way you calculate area would be different on either side of that intersection point, which motivates us to divide up the region as I've just shown here. After all, the total area then can always be found by adding together the areas which I've called A1 and A2. Let's start by calculating A1. To do that, we can bring back our sample rectangle in that region. And remember that the area of this rectangle is what we call dA1, and like any other rectangle, that's calculated as height times width. Remember that to get the height, we need the y-coordinate of these points at the top and the bottom. And the point on the top is located on that red curve, y equals x. So as I said before, the coordinates of that point would be x comma x. The point at the bottom is located on the curve y equals 0, so that point has coordinates of x comma 0. Now that we have these coordinates, we can get the height of our rectangle, and since that's a vertical distance, it would be the difference between these y coordinates. At the top, the y coordinate is x, and at the bottom, the y coordinate is 0. And of course, x minus 0 is the same thing as x. This is our height. So we can use that to go back to our formula for dA1. We've just put in the height as x. But what about our width? Well, remember that the width of this rectangle is an infinitesimally small change in x, and that is what we call dx. So this completes our formula for dA1, but that's just the area of one sample rectangle. To get our total area, we still need to add all the sample rectangles together, which is signified by taking the integral as discussed in the previous video. But what should our integration limits be? Remember that those indicate the position of the first and last rectangle respectively, so let's look over to our diagram. If we scan this region from left to right, our first rectangle would be located here at x equals 0, and our last rectangle would be located here at x equals 1. And that means that 0 and 1 should be our integration limits. But actually, how confident are we that this is x equals 1? I just actually kind of eyeballed that from the diagram, but that might not be completely accurate. So to find out for sure, we should actually calculate this intersection point properly. And the way to do that is to set these functions equal to each other, as you may remember. When we do that, we get this equation, x equals 3 minus 2x. And from here, it's just a bit of basic algebra to solve for x, and we do indeed find that x equals 1, which verifies that my integration limits are accurate. So now that we know they're accurate, we're ready to calculate our area using the formula that we came up with for dA1. Now, this is a really easy integral to calculate, so I'm going to leave it to you to check the remaining details, give us a value of 1/2. Now we need to calculate A2. So let's bring back our sample rectangle from that region. We're going to label the coordinates at the top and bottom just like usual for this rectangle. For the top point, we use the blue curve to get our coordinates. And for the bottom point, we use the green curve. So I'll pause here and check if necessary that these are the coordinates that you'll get for this rectangle. With that, we're ready to figure out the dimensions, our height and width like usual. The height, being a vertical distance, is going to be the difference between these y coordinates, just like usual. The y coordinate is 3 minus 2x at the top and 0 at the bottom. So the difference of these is our height, which simplifies to 3 minus 2x. As for the width, that would be a small change in x, which is what we call dx, and so multiplying height times width gives us this formula for dA2. Next up, we need to add together all our sample rectangles, which is signified by integrating. But we still need to specify the integration limits. So the first rectangle in this region would be located at x equals 1, so that would be our lower limit. And our last rectangle would be located here at this other intersection point. To figure out which point that is, we once again need to set these curves equal to each other, and then solve for x just using a bit of simple algebra. So that gives us 3/2 as the upper integration limit. Now, using the formula for dA2, we're ready to calculate this integral. The details of that part are pretty straightforward, so pause here and check all this for yourself to verify that the result is 1/4. As a final step, don't forget that we still need to add A1 and A2 together to get our total area. We found values of 1/2 and 1/4 for those respectively, and so that means our total area in this case is 3/4 square units. The example we just did required us to divide up our area into 2 regions, but it turns out there's a way to avoid having to do that, so let me show you how. So the method we've been using so far involved use of what I would call vertical rectangles, in that all the rectangles we've been using have been tall and thin, so kind of vertically oriented. But it would also be possible to use horizontal rectangles instead. So what do I mean by that? Well, basically imagine using rectangles that look like this instead. If we orient our rectangles this way, we could say that the width is actually a small change in y, and that's what we would call dy. But remember too that this is just one sample rectangle, and we actually want to imagine that there are a whole bunch of these rectangles, actually one rectangle for every single value of y. So we should use the variable y like I've done here, just to represent the position of our sample. But what's the advantage of using horizontal rectangles like this? Well, remember that our computation of area requires us to look at the point on each end of the rectangle. But what you'll notice is that the right end of our rectangle is on the blue curve, and the left end is on the red curve. And the same would be true for every other horizontal rectangle I build across this region. That's the case for this one sample, but if you drew any other horizontal rectangle anywhere in this region, it would always be the case that right is on blue and left is on red. And so that means we don't need to divide up the region like we did when we used vertical rectangles. Still, we're going to need the coordinates of each of these points, but you should keep in mind that we're now doing everything in terms of y. And that's important because our width will end up giving us a dy integral rather than a dx integral. So everything needs to be in terms of y for that reason. Now, the easy part here is actually the y coordinate, because y in terms of y is just y. But what about the x coordinate? Well, the equation of this curve will tell us the relationship between x and y. We want to know what x is equal to, so really just rearrange this equation with a bit of basic algebra, and that will provide you with x in terms of y. So copy that down as your x-coordinate, and you're done with the coordinates of this point on the right. Now we also need to look at the point on the left and get those coordinates in terms of y. So again, y in terms of y is just going to be y. But to get x in terms of y, we need to look at the equation of the curve to see what x is equal to. In this case, the work is done for us though. Y is equal to x, so x is equal to y. And so we insert that as our x-coordinate. Now, all of this is necessary information in order to get the height of our rectangle. The important thing to notice now, though, is that this height is a horizontal distance, so it's going to be a difference of x-coordinates. And we should always go right minus left to ensure that the height is a positive number. So x-coordinate on the right minus x-coordinate on the left. On the right, our x-coordinate was 3 minus y over 2, and on the left, it's y. And now that we've got our height and width, we can multiply them together to form dA. Next, we integrate this expression to signify the adding up of all these rectangles. But we still need to know these integration limits, and keep in mind that they're going to be y values in this case, and that, like usual, they're going to represent the position of our first and last rectangle. So scanning this region from bottom to top, we can see our first rectangle would be here at y equals 0, and our last rectangle would be here at what appears to be y equals 1. But to be certain, we need to look at this intersection point more carefully. Again, we can't just trust that eyeballing that coordinate is going to be accurate. Earlier on, we already confirmed that the x value of that point is 1. But what about the y value? Well, that point is on the curve y equals x, and so if x is 1, then y is also 1. And that confirms this as our integration limit. So let's go back to our integral and use these values of 0 and 1. All that remains now is to calculate this integral. Pause and try it for yourself. I'll show the details right away, so make sure you're ready before continuing. So first remember that fractions are problematic when finding antiderivatives, and so as a first step, I would suggest that you split this fraction up into 2 terms. The next thing I notice is that the last 2 terms can be collected together, and negative a half minus 1 gives negative 3 halves, so this is what we get. Notice now that both terms have a factor of 3 halves, so I can pull out that common factor and bring it in front to make things easier for me. And at this stage, all that remains is to take an antiderivative, which, from that point forward, this is pretty straightforward. So you can pause here and check the rest of the details for yourself. But do notice that the answer we get is the same one as the one we got before by using vertical rectangles, which is cool and also reassurance that we didn't make any mistakes. Let's try one last example. I always suggest you start with a really good sketch. In this case, the enclosed region looks like what you see in front of you here. But now we need to make a choice. Do we want to approach this problem using vertical or horizontal rectangles? So I want you to pause and think about that, and when you're ready to be spoiled, let's continue to look at the solution. I hope you were able to see that horizontal rectangles are the better choice here, and the reason is because of this intersection point. The curve that defines the bottom of a vertical rectangle would be different depending on the position of the rectangle. Whether that rectangle is to the left or right of that intersection point. So that would require us to divide up our region, very similar to how we saw before. On the other hand, for a horizontal rectangle, the right end would always be on the green curve, and the left end would always be on the blue curve, no matter which sample horizontal rectangle you look at within this region. So that being the case, horizontal rectangles are the superior method here. They'll both get the job done, but in my opinion, this is easier. Now, remember that the letter y will be used to designate the position of our sample, and dy will designate the width. Like always, we need the coordinates of the point on each end. So in this case, we need them in terms of y, since we're building a dy integral. So keep that in mind. Y in terms of y is just y. And like before, to get x in terms of y, we need to look at the equation of the curve that this point is on. A little basic algebra there shows that x is equal to y plus 2. And so we insert that as our x coordinates. Now for this other point, again, we want the coordinates in terms of y. Y in terms of y is y. And x in terms of y is given by this equation that this point is situated on. We see that x is equal to y squared, and so that's what we'll use as our x coordinate. Now we're ready to calculate our height, which in this case is a horizontal distance, and so a difference of x coordinates will do the job for us, right minus left. On the right, our x coordinate is y plus 2, and on the left, it's y squared. So there's our height, and we can multiply that by our width to get our formula for dA, which is the area of our sample. And finally, adding together all our rectangles to get the total area is now signified by taking the integral. We still need our integration limits though. Those represent the position of our first and last rectangle like usual, and we can see that both of those are located at intersection points. So we need to set these curves equal to each other in order to find those coordinates. When we do that, we'll end up with this quadratic equation, and that can be solved by taking all the terms to one side. After doing that, you can either factor or apply the quadratic formula, whichever you prefer, and you'll come up with these intersection points. I'm going to label those on my diagram just so that it's clear what my integration limit should be. And now after doing that, we are ready to calculate our area. I'll leave it to you to check these remaining details to confirm that the area is 9/2 square units. And that's all I have for you for area between curves. So I will wrap up the video here, and I'll see you next time.